Okay, in the last lecture, we discussed what we called the hypergeometric distribution, which was what? Don't let the fancy name intimidate you. It was simply a formula for calculating if you have a group of objects and you are going to draw a certain number without replacement, and if you call drawing one kind of thing a success, then the hypergeometric distribution was simply a formula for calculating what is the probability of getting a certain number of successes and the rest failures. And we did the example, you have 52 cards, you're going to draw 5. What's the probability of getting 2 aces and 3 non-aces? And there was a formula for that. And that formula has a fancy name, but you don't let the name intimidate you. Okay? All right, today we're going to do the binomial distribution and the geometric distribution. Again, they're just fancy names for very simple formulas. Okay? So, the binomial distribution is where you have an experiment and there's only 2 possible outcomes. You can call them success and failure, or you can call them heads and tails, like if you're flipping a coin, or maybe you're rolling a die and you only care about, do I get an even number or an odd number? Then you could call the outcomes even and odd. Okay, so success, failure, heads, tails, even, odd. You're doing an experiment where there's only 2 possible outcomes. Okay, those kinds of experiments are called a Bernoulli process. I better write this one down. A Bernoulli process is an experiment with only 2 possible outcomes. And then I'll put in parentheses, or not parentheses, but I'll just list them here. Success, whoops, that's not how you spell it. Success versus failure. Heads versus tails. Even versus odd. Whoops. Okay, yes versus no, etc., etc. Now you can always use these words, success and failure. Even if you're doing heads and tails, you can just say, okay, we're going to call heads a success and tails a failure. There's no positive and negative connotation there. It's not like one's better than the other. Okay? If that bothers you and you like tails better than heads, and you don't like the fact that someone's calling heads a success and tails a failure, then you can call tails success and heads failure. Okay? Success and failure in probability are not, there's no positive or negative connotation between them. It's just, you're wondering what's the probability of something happening. We just call that thing a success, and then whatever's not that is called a failure. Okay, it's just a name, that's all. Okay. Now, if you're doing that kind of a process and you want to calculate the probability of getting X successes in an trials, then we have a very simple formula for that. the probability of seeing X successes in n trials is equal to, and choose X, which we talked about last time, so you know what that means, times p to the x, so I need to tell you what that is. What is little p? Well, okay, first of all, you might say, oh, well, you've already used that letter here. You're right, and so I'm going to change that letter, and we'll say b, okay? It is a probability, and usually we use p for probability, but we're going to call this b. You'll see why in a minute. So n, choose x, times p to the x, so I need to tell you what p is. So where p is the probability of success in one single trial, and then we multiply that times q to the n minus x, where q is 1 minus p. And that's the probability of getting a failure. And the reason why we call that b of x is because this is called the binomial formula, and this is a binomial distribution, or binomial probability density function. Remember, I used those words in the last lecture. So let me show you how to use this. Okay, suppose you're going to flip a coin 5 times. What's the probability of getting 3 heads and 2 tails? If we flip a coin 5 times, what's the probability? So I said, just a second, of getting, so I said, what's the probability of getting 3 heads and 2 tails? But that's one of the beauty about a Bernoulli distribution, is where there's only 2 possible outcomes. I don't have to say what's the probability of getting 3 heads and 2 tails. I can say what's the probability of getting exactly 3 heads, and then that automatically means the other 2 would have to be tails, because that's the only other possible outcome. You see what I'm saying? And so in this case, we are calling a heads by the word success. And so I'm saying, what's the probability of getting exactly 3 successes, right? So in other words, b of 3. Okay. So how many trials are we doing? Well, it says flip a coin 5 times, so we're doing 5 trials. What is x in this case? It says exactly 3 heads, so x is 3. What's p? P is the probability of getting a heads in one single flip of the coin. Well, I think you know that that's a half, right? And we raise that to the power x, which is 3. And then we have times q. Q is the probability of getting tails, which is also a half. It's just 1 minus p. So 1 minus a half is a half. And we'll raise that to the power of n minus x. So that would be 5 minus 3, which is 2. Okay, and so we have here, remember how to do 5 choose 3? It's 5 factorial over 3 factorial times 5 minus 3 factorial. And then we're multiplying that times 1/2 to the third, and then times 1/2 squared. Remember how to do factorials. If you don't, you need to go back and watch the previous lecture again. Okay. This is going to be, here, I'll write it actually over here. This is the number 10. This is the number 1/8. This is the number 1/4. And so our answer is 10 over 32, which we can reduce to 5/16. That's our answer. If you flip a coin 5 times, the probability of getting 3 heads is 5/16. See, it's pretty straightforward. That's a heck of a lot easier than doing this. What would have been my other option? My other option is to write out all of the possibilities, which is 5 heads, heads, and then heads, and then heads, and then heads, and then tails, heads, and then heads, and then heads, and then tails, and then heads, and so on and so on and so on. Here's the thing. There would have been 32 different possibilities. And then I could have counted how many of those possibilities have exactly 3 H's in them, and I would have found 10 of them. But writing out all 32 possibilities would be a pain. So this formula gets us the answer much faster. Okay, let's do another example. It says, you play a game where the only possibilities are win or lose. The probability of winning at any specific time is 55%. Okay? If you play the game 20 times, what's the probability that you will win 15 of them? Okay, let's write this down here. And it's important to say that when you do this, the trials must be independent. Like when you're flipping a coin, you know, whether I get heads and tails on the flip has nothing to do with what happened on the last flip. That's important. So maybe I should say up here where I said what a Bernoulli process is, I should say a Bernoulli process is an experiment with, maybe I should have said independent trials with only 2 possible outcomes. Okay, so here it is. Suppose you are playing a game whose only outcomes are win or lose. Okay. The probability of winning is 55%. I don't need to tell you the probability of losing. You already know it must be 45%. Okay? So each play of the game is independent. So winning or losing is unrelated to whether or not you won or lost last time. Okay, now here's the question. If you play 20 times, what's the probability of winning 15 times? They mean exactly 15 times, but that's not the way it's written in the book. It just says winning 15 times. So when it says that, let's assume that they mean exactly 15 times. Okay? All right, so that just means we just do b of 15, and we just use the formula. How many times are we playing? 20 times. How many times are we asked about winning? 15 times, so we write 20, choose 15. What's the probability of winning each time is 0.55, so we do 0.55 to the power of what? 15 times the probability of losing, 0.45 to the power of 20 minus 15. And that's going to be giving us our answer. So we have 20 factorial over 15 factorial times 5 factorial times 0.55 to the power 15 times 0.45 to the power 5. Now this is a calculator problem. I'm not expecting you to multiply 0.55 out by hand 15 times. I'm not expecting that. Okay. I'm not expecting you to do 20 factorial over 15 factorial times 5 factorial by hand either. But I hope that you understand what I said last time about how there is a lot of cancellation that occurs in calculations like that. But it's still going to be a big multiplication problem left. So we put it into the calculator and we get here 15,504 times 0.55 to the power of 15 how many decimal places would I write here? I don't know, maybe let's just write 6 decimal places. Okay, here I'm going to put parentheses here for the multiplication. So 0. It's a really small number, that's why I said 6 decimal places, because it starts with 0.000 before we get into anything interesting. And then there's a 1, and then a 2, and then a 7, and then a 4. So when I round it off, it'll be ending with a 7 there. Okay? And then 0.45 to the power 5. We'll do 6 decimal places here as well. 0.01845. And then there's a 2 followed by an 8, so when we round it off, we'll have 3. Okay, and let's multiply these numbers together. Now keep in mind, because I rounded off, then this answer is going to be a decimal approximation. It's not going to be the exact answer because I rounded the decimals off. So in reality, I should probably put here approximately equal to. Okay, and I will also round off my answer to, let's do it this time, 5 decimal places. 0.0363, and then there's a 3 and a 4, so that rounds off to 3. And so there's our answer. Okay, so I would say there is a 3.633% chance of winning 15 of the 20 times. Okay, I think that's pretty straightforward. There's other examples in the book, but they're all just as straightforward as this. So I'll leave those examples for you to look at. Okay, let's move on and do the next topic here, which is called, that was called a binomial distribution. Okay, now we're going to do what's called a geometric distribution, not to be confused with what we did in the last lecture, which was called the hypergeometric distribution. But again, the names, I don't want to say they're not important, but what I'm trying to say is they're just names. Don't be intimidated by the fancy names. Just know the formulas, okay? And know when to use which type of formula. Okay, now, in the book on page, what is this, page 209, this section is 4.3, and it starts halfway through the page, and they give a lengthy explanation of what we call a geometric distribution, okay? And you can read that, and you should read that. I'm going to explain it using different words to try to make it a little bit simpler, okay? The explanation in the book's a bit lengthy, and it's good, but I'm worried that some people might get lost in the wording, so I'm going to explain it using different words that will be a little bit simpler. Okay, so I'm going to word it like this. Suppose we are doing Bernoulli trials. I believe that's the terminology we used, wasn't it? Oh, we used the word process. Okay, so I'll use that same word. Suppose we are doing a Bernoulli process. Let me throw in the word a Bernoulli process. And we are simply measuring how many trials it takes to get our first success. Okay, and then we ask the question, what's the probability of getting the first success on the xth trial? Okay, the formula for that is surprisingly straightforward, and it is simply 1 minus p. Remember, p is the probability of a success in one trial, okay? So 1 minus p to the x minus 1 times p. That's the formula, okay? And this is called the geometric distribution. It would make sense to me if we called that g of x, but I'm going to stick with what the book does, and it's using capital P. Okay, and something else too. I was thrown off by this when I was a student. Sometimes people write, instead of just p of x, they write p of capital X equals x. Like instead of saying p of 2, you might see it written p of capital X equals 2. All right, either way is fine. Don't let that throw you off either way. Okay, so let's do a couple of examples of this. Suppose you're flipping a coin. what is the probability that your first heads won't happen until the 7th flip? Suppose we are flipping a coin. What's the probability of getting the first heads on the 7th flip? Probably pretty small, because that means getting 6 tails in a row. So it's probably going to come out to be pretty small, but we don't have to guess, we can find out for sure. So I'll write probability of x equals 7. Okay, and again, it's an easy formula. There it is right there. 1 minus p, where p is the probability of getting a heads, which is a half. So we write 1 minus a half to the power of 7 minus 1 times a half. So let's see what that's going to be. That's going to be a half to the power 6 times a half, which is, I know, is a half to the power 7, but I'm just going to keep them separate. Okay, so that's 1 over 64 times a half. So that's 1 over 128. See, that's a pretty small number. So it's a very small probability of getting 6 tails in a row and getting your first heads on the 7th flip. Is a pretty small probability. Okay, let's do this example. Suppose you're checking computer components in a factory to see if they are defective or not. Okay, so you are randomly selecting computer components and checking to see if they are defective. This is kind of funny. The wording here would be strange, because you would answer the question yes if they are defective. And so in this particular case, being defective would be considered a success, because that's what would cause you to answer the question with a yes, which is kind of weird to think of being defective as a success. But again, you shouldn't think of it that way, because then I'm putting a positive negative connotation on there, and it doesn't have a positive negative connotation on the word success and failure when you're doing probability. Okay? All right, so suppose the probability of any one component being defective is 0.02. Okay, what is the probability that the 7th component is the first defective one? Okay, so again, that's just the probability of p equaling 7 will be 1 minus 0.02 to the power of 7 minus 1 times 0.02. Very simple formula. So this will be 0.98 to the power 6 times 0.02. That's a calculator problem. Okay, and the answer comes out to be, we'll do 4 decimal places here. So let's put approximately, since I'm rounding off, and it's going to be 0.0177. So there is a 1.77% chance that your 7th component is the first one that you find that's defective. Okay, but now I want to show you how to do one more type of question. Let's do a follow-up here that says, here's how the question will be worded. How many components do you expect to test until one is found defective? How many components would you expect to test until one is found defective? This is a different kind of question. In the last question we said, pretend that you have to test 7 of them in order to find one defective. What's the probability of that happening? Now this one, I'm not asking you to calculate a probability. Okay? What I'm doing here is I'm saying, you're just now starting to test them. You don't know how many it's going to take before you find a defective one. How many do you expect you might have to test before you find a defective one? And you might say, well, that's a matter of opinion. But the point here is that we can actually put some calculations to this, and you don't know yet how to do that because I haven't explained it. I'm going to tell you right now. Okay, the answer is something like this. You might say, I'm just going to work our way up to this, okay? You might say, well, yesterday it took me 5 tries to find a defective one, and the day before that it took me, let's say, 8 tries, and the day before that it took me 9 tries. Okay, let me write that down because I know it's hard to keep that in mind. Okay, so I'm just working this out as a hypothetical situation for you. Okay, we might say yesterday it took, I already forgot the numbers I said a minute ago, so I'll try to remember, but I might end up writing down different numbers. Let's just go with what I write down. I think I said 5. Okay. And the day before it took 8. And then the day before that it took I think I said 9, but let's do 8 again because the math will work out easier. Okay, so you might say this. You might say, judging by that, the average was 5 plus 8 plus 8 over 3, which is 21 over 3, which is 7, which has nothing to do with the fact that our last question had a 7 in it. That's just coincidence, okay? So you would say, I would expect to sell 7 components before I accidentally sold a defective one. Or, sorry, not sell, test. We're just testing these things. We're not selling them yet. So you might say, okay, I would expect, on average, that I would test 7 components before I found a defective one. Because on the last 3 days, I kept track of how long it took, and then I just averaged those, and I came out with 7. Okay, the point I'm trying to make here is that the answer to this question is the average of all possibilities. Okay, that's what I'm trying to do. Then we'll talk about how do you calculate it, but I'm just trying to get across the point that the proper way to do this question is to say, I would expect to test whatever the average is. Okay? So let's write this down. The answer is the average. I'm going to go ahead and erase these examples here now. Of how long it usually takes. Okay? Now, do you remember that we use mu for average, right? Of all possibilities. So what I just did in that example a minute ago was I only looked at 3 possibilities, which means that was a sample of all the possibilities. So in that case, I wouldn't have used mu. I would have used x bar. That's the average of a sample. Okay? But that was only taking into account the past 3 days. If you want to take into account every single day, then you're not just looking at a sample, you're looking at an entire population. And so we use mu. Okay? Now, that brings up the question though, how do you calculate the average of this sort of thing? And I'm going to give you the formula right now. It's really, really surprisingly simple. It is 1 over p. So in our case, that would be 1 over 0.02, which happens to equal 50. So on average, if there is a 0.02% chance, take that back, not 0.02%. I mean, if there is a 0.02 probability of a component being defective, then you would expect, on average, to test 50 components before you found a defective one. Okay? There is some stuff here in the section about variance and standard deviation. I don't want to get into that right now, really, but I think I will just show you the formula, since I have shown you for the formula of average here, then I guess it makes sense to also show you the formula for standard deviation and variance, because remember, many lectures ago I introduced those words to you together. Mean, which remember is just another word for average. So we introduced mean, variance, and standard deviation at approximately the same time. So since I gave you a formula here for the mean of a geometric distribution, I'll go ahead and tell you the formula for variance, which remember we call sigma squared. For a geometric distribution, the variance is 1 over p times 1 over p minus 1. I don't want you to worry right now about variance and standard deviation and what they mean. It's just I'm showing you the formula just in case the homework says calculate the variance. Okay, now you have a formula for it. Okay, and the standard deviation is always the square root of the variance, and so the standard deviation is the square root of that, and we just call that by the letter sigma. Okay, if you do have further questions about that, please come to the chat and ask me on Monday, Wednesday, Friday at 11 o'clock.